But I guess we can get started.
Hey,
So,
welcome everyone to CBE for review.
Yep, just so you know, this is recorded, so it's on YouTube afterwards. So we won't say any names.
No, we won't.
No, and I don't think there's any video. They're just recording the screen, anyways.
It's just a screen. So feel free to ask any questions, and your voice will be recorded, but not your face or name.
Okay.
Yep. So questions are welcome.
Please.
But we'll get going. Oh, also, I'm Hunter.
My name's Emily.
Yeah. So we're recitation leaders for 1050. So CBE 4 goes over these 5 general things: solving rational inequalities, exponential functions, logarithmic functions and their properties, and then solving exponential and logarithmic equations, as well as exponential and logarithmic models, like growth models, decay models, stuff like that. So first off, solving rational inequalities. So rational inequalities. You cannot multiply inequalities by a variable because we don't know if the variable is positive or negative. Use addition and subtraction to get 0 on one side of the inequality. Then you simplify into one fraction. Solve for the numerator and denominator equals 0. Test the intervals and think about if the point should be included or not. Well, that last part saying is if it's in the denominator, let's say it's less than or equal to 0. If it's in the denominator, that doesn't mean it's equal to 0. It means it does not exist. And a lot of these will make sense as we go through the example.
Like a basic strategy.
Yeah. So we have this inequality here. We have 3 over x plus 1 is less than or equal to 21 over x plus 9. And I love how they give us absolutely no space on this slide to write this.
We gotta go to the right, I guess.
That's one suggestion.
I'm gonna write this down.
But so this first point, what it says is use addition / subtraction to get 0 on one side. And so I'm going to subtract the 21 over x plus 9 so that we get it on the left-hand side. And so we're left with 3 over x plus 1 minus 21 over an x plus 9 is less than or equal to 0. Okay, so that's that first step, is you want to get everything on one side. Second step, it says to simplify to one fraction. So to do that, we need to find a common denominator. And so in this case, we see one of the terms has an x plus 1 in the denominator, another one has an x plus 9. So our common denominator is going to be x plus 1 times x plus 9. And so you have, can I zoom? Oh, I can zoom in. So you get a 3. So if you have a 3 over an x plus 1, that one needs to be x plus 9 needs to be added or multiplied by that so that we have the common denominator. Then the 1 you have plus 1 times by x plus 1 x plus 9, and then the x plus 1 x plus 9 in the denominator. And then we have minus 21 over x plus 9. And so we need to multiply by an x plus 1 in both the numerator and the denominator. And then that's all less than or equal to 0. So now that we have a common denominator, we can combine them together into one fraction. And so we'll have, I guess we can multiply this out. And so this first term will become 3x plus 27. And I'm just going to go ahead and put this all over the x plus 1 x plus 9 already. So we have 3x plus 27, the second one. If we have an x plus 1 times an x plus 9, that's going to become x squared plus 10x plus 9. And then this last term, you have a minus, and whenever there's a negative, it's important to make sure that you distribute that negative every term. That is a very common error that I even make a lot of times. And so you can either do it where you leave it outside the parentheses. So if we did like a minus parentheses 21x plus 21, or you can go ahead and distribute that negative when you do it in that step. So if we were to simplify this down, you get an x squared, you have a 3x, a 10x, and a minus 21x. And so that leaves us with a minus 8x. You have a 27, a 9, and a negative 21. So 27 plus 9 is 36. Minus 21 is 15. So you get plus 15 all over x plus 1, x plus 9. And that's all less than or equal to 0. Now we want to figure out, this next step says solve for the numerator or denominator when it equals 0. And so the easiest way to do that will be if we factor it, because then if any of those set of parentheses is equal to 0, then the whole numerator will be 0 or the whole denominator will be 0. So this factors.
Is this for the CBE for?
Yeah. Let's see, this numerator will factor and become an x plus, or an x, let's see if I can, x minus 5 minus.
If you click on the top, it's.
Well,
Don't show you.
yeah.
It is handy to be able to erase.
There we go.
You have to mess with it, and then you have to click back into it to find the pen again.
All right, let me just redo that. No, it should be.
Oh, it was red. There we go.
Welcome in.
Hey,
For review.
no, I just came to pick up my laptop. It's never gonna be closed at like.
Okay. Sorry, that was a slight delay. But so the numerator will factor to an x minus 3 and an x minus 5. And the denominator is already factored. Less than or equal to 0. And so now we need to figure out when the numerator or denominator equals 0. And those are kind of critical points that you have to keep in mind on a number line. So I'm going to draw the number line up here at the top because that's where I have the most space. Our critical points are, so what's going to make the numerator 0 is 3 and 5. And what makes the denominator 0 is -1 and -9. So if we put those in our number line, you have a -9, -1, 3, and 5. So now we need to figure out where it's going to be positive and where it's going to be negative. And so you can pick a point in between in each of these sections on your number line and plug that number into this equation and figure out whether it's positive or negative. And so if we were to take a -10, so that'll be in the far left section, and we plug it into this equation, then you have -10 minus 3. That gives you -13, so that's a negative number. And then, so this is if we had -10, x equals -10. So you get a negative number for the first thing. The actual number doesn't necessarily matter, and I'll show you why in just a minute. So you get a negative number there. This x minus 5, if you plug in negative 10, that's also a negative number. And in the denominator, negative 10 plus 1 is a negative number. It could be negative 9. And negative 10 plus 9 is negative 1. So that's a negative number. Now if we were to multiply those all together, a negative times a negative is a positive. And in the denominator, negative times a negative is a positive. And so then you end up with a positive number. And so in this section over here, we have a positive number. Oh, that was bad. Positive sign. Oh. Why does it? Fine.
You have to like press.
You have to like press?
Yeah.
I was pressing.
Okay.
Oh, wow. Oh, there we go. Positive. Okay, and then you do the same for each of the sections. And so if we go in between a negative 9 and negative 1, we could plug in something like an x equals negative 2. And in that case, if we just plug that into here, you get that the negative 2 minus 3 is negative 5, so that's still negative. Negative 2 minus 5 is negative 7, so that's still negative. Negative 2 plus 1, that's also negative. And then negative 2 plus 9, that becomes a positive. And so when you have 3 negatives, you'll have a negative. And so you can do that for each of these sections. And then what you'll end up with is you'll have a positive, negative, positive, negative, positive. And kind of as a hint, if all of them are to the power of 1, it's just going to alternate all the way through. So if you find one of them, then it'll alternate all the way through. But if one of them has a squared to it, then that trick doesn't actually work. But at that point, you would just kind of copy what you have.
So for those of you on YouTube, I recommend graphing it to see, like, okay, I cannot switch between positive values and negative values if I don't touch the x-axis or have a vertical asymptote. And so that's why we don't. Another reason. You can see it on the graph.
Yeah. If you do want to understand these graphs, like what's going on, then if you graph it, it does help quite a bit. But basically, once you have your number line all like this with positives and negatives, then you figure out when your inequality is going to be satisfied. So in this case, we're looking for when it's less than or equal to 0. So therefore, when it's negative, so that's going to be in this section and this section. And then you'll look at the endpoints of these sections. So we'll go with this first one, negative 9. At negative 9, because that's making the denominator equal to 0, it is not going to be in our interval. So that'll be a parentheses. We'll have parentheses, negative 9. If we test negative 1, that's also making the denominator 0. And so that one will also be in parentheses. Union that with the 3. The 3 is making the numerator 0. And so therefore that is in our domain. Why is it not like this top? 3 to 5. And the 5 is also in our numerator. And so that's included. Okay. And so our solution down at the bottom is kind of messy, but it's our negative 9 to negative 1 union with 3 to 5. So that's how you solve for inequalities.
How do you guys feel about that? We are. Alright. Okay. Also, this recording will go on the YouTube channel, but it's not video recorded, so just your voice. So we won't use your name. Okay. Feel free to ask whatever questions. Okay. All right. Let's go. Exponential functions. Ready? Go. Okay. I'm gonna throw this at you. This whole slide of things to remember. You don't have to write them all down. Instead of talking through them, I'm just going to write down some examples. What if I had 4 to the 2 times 4 to the 1? That's the same as 4 to the 3. 2 plus 1 is 3. What if I had 3 and 2 to the 4? That's the same as 3 to the 4 times 2 to the 4. And then we've seen this one a lot. I just wrote the same thing. What if I had that? I can write it lots of different ways. Okay. We've also seen this next one with some logarithm kind of stuff. It looks similar to a property we use a lot. Do you want me to do an example for any of the other ones? This one's also really important. We've talked a lot about how x to the 1 root 2, where we don't really write the 2 usually, is the same thing as the square root, which means x to the 1/2. Okay, good things to know. All right, so to do some of these questions on the CBE, we need to know things about our parent graph. We need to remember like basically what it looks like by remembering some important points. I didn't draw that very well, but pretend my my scale was better and maybe we could get somewhere. So I'm going to be rebellious and change the ink. So we know that it has the point 0, 1. If we're talking about a graph that hasn't been shifted at all, we also know that it has the point 1, comma a. Because if I plug in a 1 right there, I will have a to the 1. And if it hasn't been shifted horizontally or shifted vertically, that it stays right there. The domain is -infinity to infinity. The range is 0 to infinity because I can't cross the x-axis, right? It's only above there, meaning it has a horizontal asymptote on the left at y is equal to 0. Transformations are written like this. You have that equation on the CBE problems, which is lovely. We're going to talk through some of the reflection stuff, all that good stuff in a little more detail. Maybe? There we go. Okay, so our task is write out the equation for the graph of the exponential function. Here are our steps. First, I need to identify any reflections. Then I'm going to think about horizontal and vertical shifts, usually using the vertical asymptote, the horizontal asymptote to identify the vertical shift. And then I'm going to use the points that I'm given, these pieces of information right here, to solve for A. So let's remember, my general form looks like this. It's either positive or negative x, plus or minus b, plus or minus c. Okay, so remembering that like the graph of e to the x is a function that looks like this, I'm going to notice that I have a reflection over the x-axis. Ordinarily, an exponential function would never even touch the x-axis. In this case, it's both pointing down and it's touching. Because if I had just flipped it, right, I would have come all along here and then gone around here. So I'm kind of seeing two things. I see a reflection, and then I also see that it's been shifted vertically. And I know that it's been shifted vertically because this line right here, this part where it looks like it's basically equal to the line y is equal to 1, is happening at y is equal to 1 instead of y is equal to 0. So that's how I get my first little piece of information. I see that it's gonna have to be a negative. Sorry. Well, I just wanted to go back one, but I'm gonna erase anyway, so. Okay. Here we go. I know that it's negative because I saw that flip over the x-axis. Not sure about x yet, not sure about b yet, but I do know it's been shifted up by 1 because we've got this y is equal to 1 instead of y is equal to 0. Now I come over and see, okay, how can I use the rest of the information? How can I use the points to determine what else I've got here? So I know that 2, x equal to 2 and y is equal to 0. So what if I plug that in and see what I get? What can I determine about my function so far? Okay, so now we get here and I see, okay, if y is equal to 0, I have some number over here and some number over here. When my words are kind of not working for me right now, you guys. So essentially I'm going to see, okay, if my b value were equal to positive 2, or if I were subtracting a 2, so I would have b equal to negative 2, I would have a to the 0, which is equal to 1. And what I want over here, I'm just going to write this out because I'm not explaining this very well. Hunter, if you want to rescue me, feel free. We're coming over here. How would you explain this step to them?
Okay. So one thing, if you remember transformations from before in some of the other CBEs, you would, let's say like you had a quadratic, you know the point 0, 0 was on that graph. And that was the vertex, and you saw where it shifted. That was where what was in the parentheses of x got moved. So in this case, you have, in your normal graph, you have the point 0, 1. But in this case, you don't have that point anymore. Instead, we have 2, 0 is that point that got shifted to. And so for your x value, that x value used to be 0 in the original, but it got shifted to the right, 2. And so therefore, it's going to become an x minus 2. Because whatever the x value is, basically with that transformation, if it shifts to the right, then it's going to be minus. If it shifts to the left, it's going to be positive. And so in this case, you would have an x minus 2 because that point that was originally 0, 1 got shifted over to 2, 0. And so the x got shifted over twice. That's how I would explain it.
I like it. That's much more
or
summarized.
If you want to do it the way she was doing it, then you could also, if you plugged in a 2 for x, then you could move that minus or that plus 1 to the other side, and then solve for that way.
That is where my brain was glitching. So basically, I often do it like Hunter explained in my head. I identify the point that is closest to the asymptote part, which is this one. And I know that it came from the original point, 0, 1, and it got mapped to wherever it's going. And then we've already identified the vertical shift, y is equal to 1. So now I can solve this equation right here because I know what is b for what is a. So I subtract 1 from both sides. Got a x minus 2. And then we come like this. Cancel out those negatives. And then I want to know what values of what values of a are valid. So I don't have enough information right here, as was pointed out again. Apparently exponentials are not my thing today, y'all. So
basically,
yes. Do you want to come write it?
Sure.
Thank you.
After you find your what b is, it was on the eraser. Sorry. After you find this is x plus or minus b plus 1. After you find what your b and your c are, then you're just left to find what A is. And finding B or C, like she said, has to do with your horizontal asymptote and that point closest to it. And so to find A, you're going to plug in this point, the 3, -3, in for your y and your x. And so you have your y is -3 equals -a to the x minus 2 plus 1. So now we can solve this equation for what a is. So we subtract the 1 over, so you're left with -4 equals -a to the x minus 2. Wait, x is, yeah, so x is 3. Wow, this really likes to switch, doesn't it? So that's 3 minus 2, because that's our x value at that point. And so then you have -4 equals -a to the first power. And so if you subtract or divide by -1, you're left with 4 equals a. So if we plug that all back in, you know that y equals -a, which is 4, to the x minus 2 plus 1, which is what you can see as the solution right there.
So what I forgot to do is to use both pieces of information that I was given.
Yeah.
I was trying to use the same point to determine something that's already kind of in the equation. You have to use both points to be able to find the equation.
There's a reason they give you 2 points.
Yes.
So you should use both
it's not
points.
determinable unless you only have one, if you only have one.
So if we're moving on from there, now we're on to logarithmic functions and properties of logarithms. So basically, well, these two things in here, you can write a logarithm as log base b, so the log can have any base. And some common ones are log base e, which is written as ln, and log base 10, which is usually just written as log. So if it doesn't have a base, assume that is log base 10. And this is key, logs are the inverse of exponentials. So just like how multiplication and division are inverses, and so if you're trying to solve an equation, and let's say you had an x divided by 10, and you're trying to solve that equation, you would, to get rid of the division, you would multiply by 10. If you have logs, if you have like an ln of 10 equals, or actually there'll be some examples of this, but if we were to do, why does it always get rid of that? ln of x equals 10. If you were to try and undo that ln, which is the log base e, you would do e to the power. And so then x would be e to the 10. And then if you were to try and undo that e to the 10, you would do natural log. Their inverses, just like multiplication and division, are inverses. And here's some properties. These are definitely key to know, and they'll be used in this next example. If you're adding two logs together with the same base, then you can do one log with the two numbers multiplied. If they're subtracted, then those two numbers are divided, and whichever log has the negative is the one in the denominator. And then if you have some constant out in front, times by it, then you can raise that power, whatever's inside that log, to that power. So these three properties are very crucial.
Yes.
And I'll show you why in this next example. So, oh, never mind, it's not quite there yet.
More properties.
Yeah, this
Do you
property,
guys remember what this one's called?
I don't know what this one's called.
Okay, the change of base formula.
No. But this one also is
It's not
important to know.
Sometimes you
The
forget.
name is not important, but this is important to know because this is problem 3 on the CBE. For some reason, these slides are old, and so they don't have it as an actual example. But on the CBE, you might be given something like log base 4 of 255. And they're trying to, and then they give you a calculator, but you can't put log base 4 in the calculator. And so then what you have to do is you would use this formula where you have log base c, and so the calculator has log base 10 of whatever is inside the log divided by log base 10 of whatever the base of the log is. And then you can plug that in your calculator and get your decimal approximation. So this one is important to know for the CBE for sure. And if you're unable to write them all down, if we're going too fast, we can go through these again, or you can watch the YouTube video and kind of get the notation as well. But here is an example. This one's like basically the exact same as one on the CBE.
Yes.
So using our properties, where if we have, for this first one, we had the property of r log base b of like x equals log base b of x to the r. Because of that, we can take the 3 from this first equation and raise everything inside that to the power of 3. So we'll be left with log base b of the cubed root of b to the 6th over k to the 4th cubed. And the cubed root and the cubed are going to cancel each other out. And so that's just going to become log base b of b to the 6th over k to the 4th. And then you have minus all the rest of it, or minus that. And plus that. Okay, now we're going to use the rules that said that if they are added together, you multiply them. So these all have the same base, b, and so whatever it has a positive log, whatever is being added together, are going to be multiplied, and whatever is subtracted is going to be divided inside of the log. So what that would look like is log base b. This first one is b to the 6th over k to the 4th. And then you multiply that, or I guess you divide that. So that's basically times by 1 over k to the 4th, b to the 8th, because that next log has the negative. So that's going to be the denominator. And then you multiply that by k to the 8th, b to the 5th. Now they're all in one log, and so we can simplify. We see that there are 4 k values in the denominator. And so if we were to combine those together, that's going to become a k to the 8th. And in the numerator, we have a k to the 8th. So those are actually going to cancel, because these 4 will cancel with that, because you have 8 in the denominator, 8 in the numerator. And so you're left with 0 k's. And then if we look at the b values, we have 6 in the numerator, or 6 times 5 in the numerator. So that's a total of 11, and 8 in the denominator. And so you'd have b to the 11th over b to the 8th, which when you simplify is log base b of b cubed. And since the base of the log and the base of the exponent are the same, they'll cancel out, and you're left with 3.
Questions about that? Alright, so now we're going to do kind of a similar thing. I'm told I need to find log base b of 1/6, and I have 2 what might originally appear to be kind of random pieces of information. What it's forcing you to do is to use these logarithmic properties because we don't know what log base b is. We just know that log base b of 5 is 1.922 and log base b of 30 is 4.062. So I want you to notice that in this fraction right here, well, first of all, I want you to notice that we have a fraction inside the log, and so that should put you in mind of this logarithmic property where I have division happening. Right? And then I want you to think, okay, I have a number on top that's smaller than the number on the bottom, and I notice that 5 is smaller than 30. And if you are, after you've done a couple of these problems, you'll probably notice that there's always going to be some kind of a simplification. In this case, 5 over 30 is the same as 1 over 6. So we're basically just going to use that information. I'm going to notice, okay, well, if I have log base b of 1/6, that's the same because these fractions are equivalent as log base b of 5 over 30. Okay, who can tell me what I should do next?
Should make it log base b of 5 minus log base b of 30.
Exactly, awesome. Okay, I'll write that out. And then maybe somebody else explain why that would be useful to me. It's probably right there, but what can I do now?
So you have the values, so we could just
Exactly. I've got those values, so I'm just gonna plug in those numbers and do some subtraction. All right, and I forget, it comes out to be negative 2.14. Like so. Questions? No? Okay. There will always be some sort of a simplification. It might not always be using this identity, but it will always be either that one or the multiplication one. You should just look and see how can I combine these numbers to get this number right there.
Sometimes they'll also include like a square root in there, and so it'll be important to remember that you can raise it to the power of 1/2,
Yes.
and then you can pull that outside of the log as well.
Yeah. Do you want me to write something like that down, or are we good? Okay. All right. Okay. Do you want me to talk through this, or you got it?
Sure. And I'll
Okay.
just do the
Okay.
example.
Okay, so we've got solving exponential equations. Use exponential properties to gather, so here's like a general strat. Use exponential properties to gather all exponents together in one. Set the exponential equal to whatever is left, everything else. Take the appropriate log to quote unquote undo the exponential, and then solve for x. I like to think of it as if I have a variable somewhere, I need to collect all the variables kind of together so that I can use logarithmic and exponential properties to quote unquote undo it, and or take the variable out of the exponential or out of the log. The same sort of deal applies with logarithmic equations. So we've got this kind of a property. If I'm raising a number to a power, and then I have that same number raised to a different power, that's like saying, okay, well, what if I have 3 to the 2? If it's equivalent to 3 to the something, then I know that that something right here, this x, whatever it is, has got to be the same thing as 2. Otherwise, the two the whole entire quantity would not be the same. So f of x is equal to g of x if a of f of x is equal to a of g of x. Sometimes this is helpful. Instead of taking it to a logarithmic form, you can just recognize that the bases are equivalent. Logarithmic equations, like I said, it's comparable to exponential equations. You're going to use your log properties to gather all the logs into one, set the log equal to everything else, use appropriate exponentials to quote unquote undo the log, and then solve for x. All right.
Okay. So here's an example where they give us some logs, and then we're solving for what x is. So like I said before, right here, gather all the logs together. So first off, I see that there's a 2 multiplied with this ln x. And so I can move that 2 inside of that log, and that'll become an ln of x squared. And then since that is added to the ln of 10, we can use our other property that says if they're added together, you can multiply what's inside the logs together. And so ln of x squared plus ln of 10 is going to be the same as ln of 10x squared. And that's going to equal 3, because that's what's on the other side of our equation. So if we're trying to undo that log, then we need to do an exponent. And so ln is log base e. So to undo the natural log function here, we're going to raise both sides to the power, or do e raised to the side, raised to that information that's in the equation. So if we had an e to the ln of 10x squared, that's a terrible 10, equals e cubed, then the e and the ln will cancel, and we'll be left with 10x squared equals e cubed. Now it's just like you would do with any of the other equations we've had throughout the semester, where, because e cubed is just some constant value, it's just going to be a decimal. And so we can solve for what x is by dividing by 10 and then square rooting it. And then you can plug it into your calculator.
How do you know that it was the positive version and not the negative version?
So that's true. If you square rooted something, then it is plus or minus. But since you're in your original equation, you have an ln of x, and you can't take a log of 0 or anything less than 0. That is one of your domain restrictions. And so we know that x cannot be negative square root of e cubed over 10, because that will not work in our original equation. And so it is only the positive version of it.
Because, right, like exponential equations have the horizontal asymptote at x equals 0, and the logarithmic equations have a vertical asymptote at x equals 0. I said that backwards. Y equals 0 and x equals 0. Like that.
This is like a 2 to the x or so, and this would be like an ln of x, something like that. So, and then like I said, you would get this, and then you just plug it into your calculator, and then you would find it is 1.4172. And now it'll be the same kind of process, but with exponentials.
Exactly. So when you look at this kind of an equation, once again, I'm kind of tracking, okay, where are my variables at? And I'm going to need to get them together. I see that they're in exponents, so I'm going to have to use some exponential properties and then probably a log property to quote unquote take the variable out of the exponent. So first of all, I don't have any domain restrictions because of this e to the 3x plus 8 in the denominator, because any variable in the exponent can't ultimately give me a negative value, or in this case, it can't give me a 0, which is what I would be worried about. So to start off, I'm just going to multiply both sides by e to the 3x plus 8. So, like so, over 20 times e to the 3x plus 8 equal to 5. Okay, and so remember, when I have two exponents being multiplied by each other, if they have the same base, which in this case we do, they're both e's, that's the same thing as 2 multiplied together all of these times, right? 3 and then 2, which means I have 2 to the 5, and I could have found that by adding the exponents together. 3 plus 2 is 5. So what I'm doing here, because I'm multiplying the e's together with their respective exponents, is I'm adding the exponents together. So I'm going to write that out. E to the 7x minus 12 plus everything over here, 3x plus 8, all that over 20, equal to 5. Okay, now I'm just going to choose to simplify that. So 7x plus 3x is 10x. And then negative 12 plus 8 is negative 4 over 20 is equal to 5. Okay, now I'd like to have just the exponent by itself so that it's a little simpler to see how to use my logarithms. So I'm going to multiply both sides by 20. All right, okay. Now, who can tell me what I should do next? Ellen, of both sides? Yes, sir. Okay, I like that idea. So if I have the natural log, I'm going to actually write it just for funsies, sort of. If I have the natural log, that means I have log base e, right? Log base e of e to the 10x minus 4 means that this whole thing has to be equivalent to whatever's in the exponent. That's what answers that question. I raise e to the what to get e to the 10x minus 4? Well, e to the 10x minus 4 has to have that exponent. That's just a number. We don't have to figure it out right now. And now we're back in linear solving for variables land. So just add 4 to both sides. And divide by 10. All right, so now we're here. I know what x is equal to. I have a candidate and I don't have any plus or minus business, so we're all good. I didn't have any domain restrictions, and your calculator will let you evaluate this. On this question, I think it does ask for a decimal approximation. I looked at it before, but your calculator lets you solve this. So
yeah, well, on the CBE, just read through the question on whether it asks for a decimal approximation or if it asks for the exact value.
Yeah, if it asks for the exact value, you can leave it like this. You don't have to do anything else. And you would type that in your calculator like this, just practicing the parentheses. Open parenthesis, ln, and it kind of gives you the automatic parentheses for whenever you have a log, plus 4, close parenthesis, divide by 10. You could type it in like that. So, okay, questions? Yeah.
Where did the 20 go?
Where did the 20 go? I multiplied. You kind of can't see it because I put the solution. It was over here. You can't really see over here. And I multiplied both sides by 20. So 5 times 20 is 100. And that's why it came over, kind of came over to the right hand side. Yeah?
All right.
Awesome. Okay. More questions? Okay. All right. Problem 7.
Okay. This one's going to use that similar property where it said like a to the f of x is equal to a to the g of x. Therefore, f of x equals g of x. So what we want to do with this is we have 9 and 27 as our bases. And so they're not the same base, but we can write them as the same base. Because we know,
common factor.
Yes, they have a common factor. Because 9 is 3 times 3, and 27 is 3 times 3 times 3. And so therefore, 3 squared equals 9, and 3 cubed equals 27. So if we were to rewrite this, we could say that this 9 to the negative 3x is 3 squared to the negative 3x. And this 27 is 3 cubed to the 2x plus 2. Now they have the same base, and we can simplify this because these are raised, this 3 squared is raised to the power of negative 3x. You would multiply those exponents. So this is a 3 to the negative 6x, And then on this side, you have 3 cubed raised to the 2x plus 2. So when we multiply that, you get a 3 to the 6x plus 6. Now they have the same bases, so we know that whatever is in their exponents are going to be equal to each other. And so we have a negative 6x has to equal 6x plus 6. If we were to solve this, we can subtract 6x from both sides. And we're left with negative 12x equals 6. You divide by negative 12, and you get that x equals negative 1/2. Any questions on that? So on the CBE, what you'll want to do is you'll want to find with these bases what their common factor is, and then try and get the same base. You see that the solution for that is negative 1/2.
Perfect. Okay, now we're going to talk about modeling of things. We're going to put those properties to use and kind of use our knowledge about the parent function as well. So these are all kind of the same thing, the exponential growth model and the exponential decay model. We've got some kind of a constant out in front. That's usually our initial value is how we think of it. We've got e to some kind of a growth rate. The growth rate might be negative if we know it's decay, if we're talking about it as if it's decay. And then we've got the dependent variable t, which represents time.
So are those two equations just the same? It's just a negative in front of them?
Correct.
Yeah.
They're exactly the same. You actually don't have to think about them as separate. You can just know that, okay, this is the growth and decay model, and it will have a negative k value if it's actually decay. So difference of magnitudes is a similar idea. They print this all the time on the CBE for you to look at and use. But basically, this is how like the Richter scale was defined. If you have some magnitude minus some other magnitude, you can talk about the difference between them on a logarithmic scale, which dramatically makes the quantities easier to write down. Instead of being super, super big, they're you can write them as a 3 or 4 decimal places. Okay.
Sorry, could you explain what each variable is in the exponential growth model?
Yes. So, initial value. I don't know if I know how to spell, but initial value. E is the growth constant, like it always is, 2.17, that'll be the same. And then R, or K, however you want to write it, is the growth rate, growth/decay rate. And T is your dependent variable.
Which is usually time, which is why they put it as a t.
Uh-huh. Okay.
It's just a 0?
What do you mean?
So it's p.
That's
naught.
a subscript. It's called P naught.
It's the whole.
Yeah.
Okay.
P sub 0 is the initial value, meaning P at time 0 is what they're trying to imply there. Or A at time 0. Like if you have a loan and you put $1,000 in at first, that's called your principal amount, and that would be P sub 0. And then you'd say, okay, it's going to grow at this interest rate over this much time. Okay, more questions?
No, that's perfect.
Okay. All right, so if we're using a model, we got to know which model to use, solve for unknown variables, and use whatever we know to find what we want. Okay, let's show that. All right, so I have a biologist puts a population of 300 bacteria into a growth medium at 8 a.m. She measures the sample again at 4 p.m. and now the population is 750 bacteria. How many bacteria will there be at 8 a.m. the next morning? Round your answer to the nearest whole number. Okay, so at the beginning, what do you guys think our initial value is?
300.
300. Okay, I'm gonna write that down. I'm gonna put it as population. Okay, and that's at time 0, right? At the very beginning. And I happen to know that the 24 hours on the clock, that's 8 a.m., What's another piece of information I have what's the next time I know what the population is?
4 p.m.
Okay. How many hours have passed since 8 a.m.? 8 hours. Okay. Just as a note, this would be the same as if it had been like 8 minutes. We could use the same equation. We would just interpret it in hours versus in minutes. As long as they're consistent, you don't have to change the equation. If it had been like minutes and then we change it to hours, then we would have a change factor. Okay, anyways. So I know that there are 750 bacteria at 8 hours. Okay, so let's write out our little equation. So here's what we got so far. E, I usually write it as K of 0. Okay, so, sorry, I was trying to write two things at once. All right, so I don't know what K is equal to yet, and I need to be able to tell you how many bacteria there are going to be at 8 a.m. the next morning. But I haven't used this second piece of information yet. So what if I used it? What would happen? At time is equal to 8, I know that the population is equal to 750. And I also know that the rest of the equation looks like this. Not sure what K is, but I do know that T is equal to 8. And now, the only thing I don't know in this equation is the K value, so I can simplify. I'm going to divide both sides by 300 to get at that K, the variable I don't know. And then I'm going to take the natural log of both sides. And then I can divide by 8. Oh. Okay. So as I'm putting this into my calculator, especially because it's asking you to round to the nearest whole number and not have 4 decimals, you could put this into your calculator and get whatever K is equal to maybe 4 or 5 decimals and call it good. Or you could wait. I don't actually know if this one's easy. Anyway.
The key with most of these probably is just keep as many decimal places. Try and stay as accurate as possible till
as long as possible, yeah. And if you want, often if I need a lot of accuracy, I don't even bother evaluating this until I'm plugging it in later. So we can do that a couple different ways. So anyway, I'll show you the next step and then it'll be a little clearer what I mean. If you wanted to, you could do a decimal approximation right here, but you don't need to. So, okay, I'm still interested in how many bacteria will there be at 8 a.m. the next morning. What will the T value be at 8 a.m. the next morning? 24, perfect. And we know that because it's been a whole day and there are 24 hours in a day. All right, and now I want to know what is P of T. So P of 24 is equal to something, but it's also equal to 300 e to the K of 24. Now I happen to know what K is equal to, so I can put that in my calculator, or I can use my decimal approximation and find that it comes out to be, when it's rounded, 4,688. So
you need an approximation for K.
Yeah. I just found it, thanks. So we could go out however far you want. And then 300 times e to the k times 24 will come out to be about this number. Questions? Okay, if I had been asked how many minutes, I would have to translate it and talk about it in hours. So,
I have a question.
Yeah.
I've seen on some of the practice, it talks about compounding.
Mhm.
Is that the same as exponential? Compounding?
Yeah. So compounding interest.
Yeah.
Yeah. So compounding interest means exponential growth. Compounding, like constant compounding interest means that it never stops, and the way we express that is with e. So,
That's how they actually, I think, found E originally was
Yeah.
with money.
That makes sense.
yeah.
Yeah.
Yeah. It was pretty cool. It has cool history.
Just some guy was like, I don't want to be paid all my interest at the end of the year. What if I did?
Why
every
don't you
6
give it to
months?
me
What
now?
if I did every 3 months? What if I did this?
Mm-hmm.
So
And because-
E is just basically like, as it gets shorter and shorter amount of time, it would like converge to what the value of E is.
So it doesn't change the equation in any sort of way if it says
If
compound.
it's compounding,
No.
no. It just means it's growth.
And then if it gives you like an interest rate, then that would be the rate.
The R
Okay.
value. Yeah.
The-
The K or
like
the R
K.
value, whatever is next to the T.
Fair enough.
If you guys want, you can pull that up and we can go over it after we're through these slides. Okay, you wanna go?
Okay. So now this one talks about magnitudes. And so you had the equation. This equation is usually given to you. You have an M1 minus M2 equals log of I1 over I2. Okay. So with that information, this problem says an earthquake in California had a magnitude of 3.15 on the Richter scale, and an earthquake in Alaska had a magnitude of 7.1. How many times more intense was the earthquake in Alaska? Round your answer to the nearest whole number. So, to determine which one we want as 1 and 2, generally, number 1, you want to do whatever the one that you're analyzing. So in this case, it says how many times more intense was the earthquake in Alaska? And so we're going to do M1, which has to do with Alaska, is 7.1. And M2, which has to do the one we're comparing it to, which is California, 3.15. And we're just wondering what the ratio is. We want to know what I1 over I2 is. So I'm just going to call that the ratio. So if we plug those back into our equation, then we find that we have 7.1 minus 3.15 equals log of the ratio. 7.1 minus 3.15 is 3.95 equals the log of our ratio. And our ratio is what we're trying to find. So now to undo our log, this is because this equation doesn't give you some base, we're assuming that it is the common log, which is base 10. So we raise both sides to the power of 10. So you do 10 to the power of that, 10 to the power of that, and then you get your ratio equals 10 to the power of 3.95. And so that is approximately, if you plug that into your calculator, 8,913. So what that is saying is that the intensity of Alaska, which you know is greater because it has the higher number, is 8,913 times more intense than the one that happened in California. even though the numbers that they report are only 3.95 apart, it's actually 8,900 times different. And so it's quite a bit. And that is your solution. Any questions on this one? I know on the test they might do a very similar thing, but with decibels. But that is the same equation, the same process.
Covers the big here about the ratio and the one that we're analyzing. More intense in Alaska, so Alaska.
Yeah.
So if it was the opposite way around, it'd be minus 8,000 something.
It would be a decimal. It basically what it would end up being is this would be 10 to the minus 3.95.
Oh yeah.
Which would be the same as 1 over 10 to the 3.95. And so the ratio would be 1 over all that. So it'd be some decimal. It's like, oh, it's this much. It's like
Less.
0.0002 times the intense, meaning it's actually less intense. So. Last problem.
Okay, I think this one is fun because we have to know what a half-life means. So, a 100-gram sample of radioactive isotope decays to 22 grams in 200 seconds. What is the half-life of the isotope? So let's write down what we know. Anybody want to tell it to me?
The initial E over K.
We've got some initial stuff. Okay, how much do I have at first?
100 grams.
100 grams, right? There's going to be an E involved somehow. What goes on the other side of the equal sign?
22.
Yeah, because that's what I get down to, right? Okay, and how fast is it happening?
200 seconds.
In 200 seconds, okay? So I've got some K value that I don't know what it is, and it's happening in 200 seconds. So here's what I've got. I want to know what is K. What is that decay rate? Or in other words, what is the half-life of, well, not quite what is the half-life, but first I need to know what is the decay rate to be able to tell you how long it will take for the isotope to go from its full amount, whatever you started with, to half of it. So first let's find K. What should I do first?
Divide 100.
Beautiful. What next? Maybe somebody that didn't answer yet.
Is it the ln?
Uh-huh. Yep, so I notice,
Both sides.
okay, the thing that I want is up in the exponent, so I gotta take the natural log of both sides. Because I'm kind of answering the question, okay, if E raised to the what is equal to the natural log of 22 over 100. So, like, I could picture this side as log base E. So E to the 200 times K is equal to 22 over 100, if you want to think of it as that kind of translation, or you can remember that the natural log and E to an exponent are inverse operations. All right, so now we're here. I think I should divide by 200 and get K by itself. All right, and I'm just gonna cheat real fast.
You just want the number.
Yeah.
It's negative 0.00757.
Like that?
Yeah.
Awesome. Okay. So that's our K value. Now I know what I'm doing. This is the exact form. That's an approximation, so I should make it squiggly. All right, so.
So that's the half-life?
No, that is the growth rate. Remind me, what does half-life mean?
When it gets to half of its original value.
Yes, half-life is an amount of time, and growth rate is a rate. It's like growth over time, so it's not the same thing. So now I need to use this k value to find half, to find the point where whatever I have will be half of what it was. You can do this a couple different ways. You can decide, okay, I want to know how long I happen to have an 100-gram sample again. How long will it take me to get to 50? You can set it up like this. I want to know if I have an 100-gram sample, how long will it take me to get to 50? I know what K is, so I just don't know what T is. So tell me what T is, and that'll be my half-life. Or you could even go a little bit more abstract. I want to know what T is if whatever I started with, I should probably not use A and P together, but whatever. However much I started with, I want to know how long it'll take me to get half of it. Like this. And once again, I know what K is. So the only variable over here is this T. And so the way I would start solving that is the same way I did that, is the same way as I found K. I divide both sides by whatever this coefficient is, and because there's 1 on both sides, I can still solve that equation. And say, okay, a sub 0 divided by a sub 0 is 1. So I've got 1/2 is equal to e to the kt. Take the natural log of both sides. I know what k is, so t is equal to the natural log of 1/2 over that whole thing of k. Like so. So it's about
91.557.
Thanks, Hunter. Say that again.
91.5573.
Awesome. Okay, so, and remind me, somebody explain to me again, why is this number right here not the half-life?
It's the rate of decay.
Yes. And how would you interpret this number? Somebody else?
It's the half-life.
What does that mean?
Means when the sample is half of what it started as.
Exactly. Awesome. Okay, that is all. And we rounded it to decimal places right there. Okay, this video will be posted on the Aggie Math YouTube channel. There will be others